Hi, this is Chunwei Liu. Today, I will introduce our work, a deep dive into common open formats for analytical database systems. This is a joint work with Anna, Matteo, and Brandon from Microsoft Grid System Lab. Modern applications and systems are generating huge amount of data every day. To process the data at large scale efficiently, most analytic database systems are backed by column file format for the extraordinary storage and query benefits. Columnar storage format store each column independently. This design greatly reduces I/O, making column database a standard to support OLAP system for big data processing. So any improvement in column format efficiency make a big impact on both research and real-world applications. Therefore, there have been a lot of debate and discussion about which format is better. Early discussion around the emergence of Arrow between Daniel Abadi and Wes McKinney, and later comparison for most popular formats. In our paper, we offer fresh insight into this critical discussion. To answer the question of which format is better, let's check out the analytic query workflow first. To answer a query, OLAP system need to load the data file from a local disk or remote storage node, which is associated with I/O and transmission cost. Once the data is loaded into memory, conversion is needed to deserialize the file into a system-specific in-memory data structure or in-memory error table. So the overhead here includes the data parsing, decompression, decoding, and the data structure building before the query evaluation. If we check the whole query workflow, there are many techniques can be used to optimize the query processing, such as data escaping, in-situ query, vectorization, and compiler optimization. So all those techniques will be covered in this paper. Let's start with column file format layout. Figure 1 summarizes a generic column file format design. So column storage format physically saves the record belonging to the same column sequentially. To achieve better data access at scale, column file format partition column into chunks. Figure A is basically a neat layout for an in-memory error table, but different format may use a different name for different layer, as shown in Table 1. In Arrow, the table is split into record batch, which include a chunked array corresponding to each column. In Parquet, the table is split into row group with column chunk for each column. The column chunk includes the data pages and the dictionary page when dictionary encoding is enabled. ORC split the table into strips, which includes the indexed data and raw data for each column. Column file formats are designed for different purposes, like Arrow is designed to be a in-memory computation format, while Parquet, ORC, and Arrow Feather are targeted as on-disk file formats. They vary a lot in terms of the encoding and the compression support, which directly impact the compression performance. Also, they have a different control granularity for the data access, which impacts the query performance a lot. Also, different OLAP systems may have a different optimization for each format. To avoid optimization bias from the query engine, we evaluate directly with vanilla API. Our evaluation includes the following dimensions. First, compression ratio over the real-world dataset and also the TPC-DS benchmark. And also transcoding performance, including the compression and the decompression evaluation. We also include the macro benchmark on some common query operations. And also we include the end-to-end evaluation over the subquery extracted from the standard benchmark. In the end, we apply popular optimization technique to show potential speedups. Let's see the compression ratio performance first. Here, we evaluate the compression ratio over several real-world datasets. This including CodecDB dataset, public BI, and GeoB dataset. You can find detail about those datasets in our paper, but in this experiment, we extract each column and convert it into Parquet, ORC, and Arrow Feather file separately. In Table 1, we report the compressed file size. Overall, we can see Parquet is best because its comprehensive encoding and compression support. Even in detailed evaluation by tab, Parquet still outperforms others. Table 2 shows the average and the standard deviation of the compression ratio. We can still see Parquet is best. Since ORC and AeroFeather has no encoding support for float, they can barely achieve any compression benefits on float columns. This observation can also be verified by the compression ratio CDF line figures shown at the bottom. In our paper, we have a detailed experiment about the data distinctness and also the compression ratio evaluation. We also get similar observation on standard benchmark like TP-CDS. We here vary the compression methods to show the compression ratio difference. These missing bars are because the corresponding formats don't support the compression. Parquet is still the overall best because it's wide support for encoding and compression. gzip is the most effective compression option, but there is a huge time overhead associated with it, which we will show it in a few slides later. Also, we provide a detailed evaluation by tab in the paper. Let's then compare the compression and the decompression overhead. Here, we evaluated the compression time overhead. In this experiment, we serialized an in-memory catalog sales table into each format. We can see the outlier here. gzip is effective compression, but with a high time overhead. AeroFeather benefits from the AeroFast serialized and deserialized interface. Also, because of its poor encoding support, it skips the encoding step, so Aero is best in terms of the writing time. Then for the deserialization cost, here we load each format, decompress and decode the file into an in-memory Aero table. Still, AeroFeather is best because of its fast serialization and deserialization interface. We have seen the huge performance difference between these formats. This difference stems from the encoding and the compression choice. So a smart encoding and compression selection based on the data statistics and the workload is critical. We are glad to see many recent work in this direction, like CodecDB and Layer. Since most column formats have a huge decompression cost, a more efficient query engine should seek opportunity to push down the query evaluation near to the file and close to the original file representation to avoid the decoding cost. We then show the macro benchmark over several query operations. We first evaluate the projection performance, where we select an integer column from the catalog sales table with a code cache. We report the runtime here. As we can see from the figure, Parquet and ORC are far more better than AeroFeather. Aero is slow because several design bugs, which we will investigate them later. Similar observation we can get for projection on double column. Parquet performs best because its outstanding compression performance, which saves the I/O overhead than others. We observe a dominant loading time during the previous evaluation, so we investigate the loading overhead for both ORC and AeroFeather. Here, we change the number of columns loaded and report the projection runtime. As we can see, AeroFeather is constant since its API requires parsing the entire battery, including all columns from disk for single column loading. Also, log acquisition is needed for each battery parsing, which is in total result into more than 90% overhead. On the other hand, ORC has a better control over the data refinement while loading. Aero also claims parallel loading, but it only parallels the decompression step, as you can see. For the uncompressed version, there's no speed up at all for the loading time. In comparison, parallel loading helps when this standard compression is applied. While we have seen the narrow and wide query performance by varying the number of columns loaded, now we investigate the query with changing the portion of column in entries that need to be extracted. Here we report the query runtime by varying the selectivity of the query. we observe almost a constant runtime for arrow feather, ORC, and optimized arrow feather with chunk level skipping, because they all require full column and chunk loading before the query evaluation. On the other hand, Parquet's streaming style API enable efficient entry-level skipping, while it suffers from branch misprediction overhead, which reached a peak at around 50%. Overall, ORC is best because it's efficient data loading interface. Let's then zoom into the very beginning of the previous x-axis with a very small selectivity. Please note, both axes are log scaled. We can see the runtime of Parquet and the optimized arrow feather quickly increase as tiny portion of the column entry are requested. This motivates some smart workload-driven partition work. We observe many work in this area like QGTree and SDC. We also include detailed filter evaluation, cold cache, and warm cache evaluation, some other runtime profiling in the paper. So here are some takeaways. We observe the trade-off exists for simple data access operations with no formatted cell in every dimension. Also, data skipping only works with a smart data partition policy and also with a fine-grained control interface. Some co-design are needed between the on-disk file format and the in-memory representation to improve the data loading efficiency. Let's then see the end-to-end evaluation. In this set of experiments, we extract this sample subquery from large TPC DS queries. The query include wide and narrow queries, high and low selective predicate, and also they cover different data types. In order to avoid interference from the query engine, we write our own query operators and interact with this column format low-level C++ API directly. Here we report the end-to-end query runtime for each query with a code cache. Overall, ORC is the best due to efficient in-memory mapping representation and more data skipping opportunity. Arrow feathers loading time dominates the runtime, slowing the query evaluation. Parquet auto-performs arrow for certain queries over large tables, but is slower than ORC because its inefficient streaming style data access interface. Later, we will show the query speedup if we apply in-memory mapping interface like ORC and arrow feather for Parquet. Here, we show the query improvement by applying each available optimization techniques layer by layer. In this experiment, we apply optimization techniques like direct query for some string column in query 2 and 3, and compiler optimization like Godiva over all queries. By applying compiler optimization, we get a reduced computation runtime, while the significant portion of the loading time is not improved at all. While the direct filtering over the string column, we can improve both the data loading and the computation time. We can get up to 4 times improvement over the vanilla version by skipping the decompression and efficient evaluation in the encoded space. Here, we optimize the Parquet performance by applying the available optimization techniques. We start with evaluating the vanilla Parquet streaming style data access API. Then we enable the bulk loading from Parquet file into arrow in-memory table before the query evaluation. We also show a dedicated Parquet in-memory mapping with the support of the latent loading. Based on that, we also show the improved performance by enable a direct query in the original encoded space. And last, we show the query speedup by vectorization. We can see using arrow doesn't improve the query performance too much because of huge data loading cost. By applying the co-design logic, a dedicated in-memory Parquet format with lazy loading improves the performance by an order of magnitude. Furthermore, with the direct query and SMD, we can get up to 100 times speedup over the vanilla Parquet interface. Please see our paper for a detailed implementation and evaluation. To summarize, Compiler-based optimization helps the query execution, but doesn't help the significant data loading overhead. While the data loading cost can be amortized by issuing repetitive queries and computational-heavy operations. The co-design logic works well for Parquet. It also proves its advantage of pushing the query down to the storage and even down to the compressed domain. Thanks for your attention. The paper has more interesting findings that I didn't cover in this short talk. Please refer to our paper for more details. If you have any questions, please drop me an email. Thanks.